If you look at the universe through the lenses of our most powerful telescopes, a strange, almost mystical pattern becomes clear. The cosmos isn't just existing, it is moving, but it isn't moving chaotically. Galaxies holding hundreds of billions of stars swirl into colossal spirals. Planets orbit their suns, while those suns hurtle in great tracks around the cores of their galaxies. Even dead, ultra-dense stars complete hundreds of rotations on their axes in the span of a single second. Everything in the universe, from the smallest subatomic electron to incomprehensible cosmic superclusters, is in a state of constant, relentless rotation. Nothing in the cosmos is truly still. And that forces us to ask one of the deepest questions in modern physics and cosmology. A question that seems deceptively simple, yet has the power to shatter our intuitive understanding of reality. Why does the universe spin at all? Where did this first impulse come from? If the cosmos had been born perfectly uniform and symmetric, everything should have simply blasted outward in straight lines or collapsed straight back into a single point. But instead, the universe chose to dance. What twisted matter into motion at the very dawn of creation, long before the first stars even ignited? Is rotation a fundamental property woven into the fabric of space and time itself? And does the entire universe, as one whole structure, spin around some invisible ultimate axis? Right now, as you watch this video, you feel a sense of absolute stillness. You feel grounded, as if the earth beneath you is stationary, but it is a profound illusion. Right now, the ground under your feet is hurtling through the vacuum of space at roughly 1,000 miles an hour just from the Earth's rotation. On top of that, the planet is orbiting the sun at nearly 19 miles per second, and the sun itself is leading our entire solar system around the center of the Milky Way at 500,000 miles per hour. We live our lives inside a colossal cosmic top. Our planet, our days, our nights, and the very architecture of our solar system are not random coincidences. They're the permanent, frozen record of a motion that set into play billions of years ago and has never, not once, stopped. Today, we are going on a journey to find out what started this grand cosmic dance. We will dive into the mysteries of quantum mechanics, trace how stars are born, explore why certain planets decided to break the rules and spin backwards, and ultimately try to answer whether the universe itself holds its own global spin. You won't need a PhD in astrophysics for this. You just need something much simpler, but far more important, your curiosity and a little patience. So, let's go back to the very beginning, to the law that rules every single turn in our reality. Imagine you're watching a figure skater. She's in the center of the ice, and she begins a spin. Her arms are out wide, her body upright, and she's turning, slowly at first, the rotation visible but unhurried. Then she does something. She pulls her arms in, draws them tight against her body, crosses them over her chest, and in that same instant, without anyone pushing her, without any new force applied, she accelerates. The spin becomes a blur. She's turning faster than before, and she did nothing except make herself smaller. When the spin ends, she opens her arms again, and she slows. Most people have seen this. Many have a rough intuition for why it happens. Something about physics, about spinning faster when you're more compact. But very few people have thought about what it actually means in the context of the universe. That skater is demonstrating one of the most fundamental laws in all of physics. A law so deep, so reliable, so woven into the fabric of reality that it holds true from the spin of subatomic particles to the rotation of supermassive galaxies. It holds true in a vacuum of space where there's no ice, no friction, no air. It holds true in the crushing gravity near a black hole. It holds in places where ordinary common sense completely breaks down. And it holds right now under you in the spinning Earth. The law is called the conservation of angular momentum. And it is, in a very real sense, the reason everything in the universe rotates. Before we go any further, we need to spend a little time here, because this concept, angular momentum, is one of those things that sounds technical, but is actually something your body already understands. You felt it. If you've ever been on a spinning office chair and pulled your legs in, you felt it. If you've ever watched the spinning top slow down when it tips, you felt it. If you've ever thrown a ball and noticed it maintains its spin to the air, you've witnessed it. Angular momentum is simply the quantity of rotation an object possesses. It depends on two things: how fast the object is spinning and how the mass is distributed. Specifically, how far the mass is from the axis of rotation. The further the mass is from the center, the harder it is to change the rotation. This is called the moment of inertia, a measure of how resistant a rotating object is to changes in its spin. When the figure skater extends her arms, her mass is far from her body's axis. Her moment of inertia is high. When she pulls her arms in, her mass is close to the axis. Her moment of inertia drops. And because angular momentum must be conserved, because the total quantity of rotation cannot simply vanish, her spin rate increases to compensate. Angular momentum equals moment of inertia multiplied by spin rate. If the first goes down, the second must go up, or vice versa. The product stays constant. The universe's bookkeeping always. Now, here's the crucial point. Angular momentum is conserved. That means it doesn't spontaneously appear, and it doesn't spontaneously disappear. If a system has angular momentum, if something is spinning, that spin came from somewhere. It was transferred from something else, or it was inherited from the original motion that set the system in place. Just as the total linear motion momentum in the universe is conserved, so is the total rotational motion conserved. This is not a coincidence or a rule someone invented. It is a consequence of something even deeper, a mathematical symmetry in the laws of physics. Emmy Noether, one of the greatest mathematicians of the 20th century, proved in 1915 that every conservation law in physics corresponds to a symmetry in nature. The conservation of angular momentum corresponds to the fact that the laws of physics are the same in every direction of space, that there is no preferred direction in the universe, no special up or down built into the fundamental laws. The universe conserves rotation because it has no preferred axis to rotate around. Think about that for a moment. The spinning of the Earth, the orb of the Moon, the wheel of the Milky Way, all of it ultimately traces back to symmetry so pure and abstract that it lives in the mathematics of space itself. So now you know the law. But knowing the law doesn't yet tell you where the spinning came from in the first place. Conservation means once you have angular momentum, you keep it. But it doesn't explain how it got started. A law that says what spins keep spinning doesn't tell you why anything started spinning at all. For that, we need to look at the universe in its earliest stages. We need to look at the conditions from which everything, planets, stars, moons, and galaxies, was eventually born. And it turns out that the answer begins not with a dramatic explosion or a divine push, but with something far more modest, a slight unevenness in a cloud of gas. This is how stars are born, or at least this is how it begins. The universe, several billion years after the Big Bang, was not empty. It was filled with vast clouds of gas, mostly hydrogen, some helium, trace amounts of other elements, drifting through space. These clouds are called molecular clouds, and they are enormous by any human measure. A typical molecular cloud can contain enough mass to make hundreds of thousands of stars. They are dark, cold, and diffuse. Their gas spreads so thin that a chamber would be considered a near-perfect vacuum by the standards of any laboratory on Earth. But they're not perfectly smooth. Here and there, within these clouds, small regions are slightly denser than the rest. The gas is a little more concentrated. The gravitational pull of that denser region is slightly stronger than its surroundings, so it begins to attract more gas from the neighborhood. The denser it gets, the stronger the gravity. The stronger the gravity, the more gas falls in. A runaway process begins. The cloud begins to collapse. Now, and here's a critical thing. All clouds rotate, at least a little, due to gravitational shearing in the galaxy's disk. No cloud of gas in the real universe is perfectly still. Every one of them has at least some tiny residual rotation, some small amount of angular momentum inherited from the motions around them, from neighboring clouds, from the slow churning of the galaxy itself. It's a tiny amount. It might seem negligible, but it is never zero. And when that cloud begins to collapse, when gravity starts pulling it inward, shrinking its radius, that tiny residual spin begins to do something remarkable. Angular momentum is conserved. So if a rotating cloud collapses, if the radius gets smaller, then it must spin faster. Even a little pre-collapse spin goes a long way. Picture it. A gas cloud the size of several light years, turning so slowly that calling it rotation almost seems generous. Barely a drift, a whisper of motion. Then gravity compresses it. The cloud shrinks. And as it shrinks, as the radius drops by orders of magnitude, the spin accelerates. Not by a little, by an enormous amount. The same way the figure skater goes from a slow turn to a blur by pulling in her arms. Except the scale here is cosmic. The radius is shrinking not by a factor of 2 or 3, but by factors of millions. A big, slowly rotating system turns into a small, rapidly rotating system. The collapse amplifies the rotation rate. But something else happens too. Not all of the gas falls straight inward. The collapse is not symmetric. As the cloud collapses, material along the spin axis can collapse onto the forming star. But material in the spin plane has its infall halted by the centripetal force generated by the rotation. A disk is formed. This is extraordinary. The rotation that was barely perceptible in the original cloud, that almost nothing spin, has, through the physics of collapse and conservation, produced a flat, spinning disk of material around a newly forming star at the center. A disk that will persist for millions of years. A disk from which planets will eventually form. The solar system you live in, the sun at the center, the planets arranged in a flat plane all orbiting in roughly the same direction, is a fossil of this process. It is a permanent record of a rotation that began in a cloud of gas long before the sun existed. The tilt of the planets, the direction of their orbits, the fact that they move in the same plane rather than randomly in all directions, all of it traces back to that original residual spin. The Earth's rotation is the memory of a cloud. And here's something worth sitting with for a moment. The sun holds over 99% of the mass in the solar system, but it holds less than 1% of the angular momentum. The sun does not spin as fast as it should, given the orbital speeds of the planets. This sounds like a problem, and astronomers do call it the angular momentum problem of star formation. If angular momentum is conserved, where did the rest of it go? The answer involves several mechanisms working together. Magnetic fields threading the disk and the forming star, bipolar jets that blast material out along the rotation axis, carrying angular momentum away with them, and the slow transfer of angular momentum outward through the disk to the forming planets. The disk, as one researcher put it, is essentially a device whose purpose is to separate mass and angular momentum. The mass falls inward to build the star. The angular momentum gets redistributed outward, eventually ending up in the orbits of planets. So the planets don't just orbit because there's a star to orbit. They orbit at the distances they do, with the speeds they have, because of an angular momentum budget that was set in a collapsing gas cloud billions of years ago and had to go somewhere. It ended up out here, in the world beneath your feet, in the moon pulling at the oceans, in the day and the night. Speaking of the day and the night, let's talk about the Earth's own rotation for a moment, because it contains a story that connects everything we've talked about to the world you experience every 24 hours. The Earth rotates once every 24 hours. That's the day. But this number is not fixed. It never was. Earth's rotation is slowing slightly with time. A day was shorter in the past. This is due to the tidal effects the moon has on Earth's rotation. Atomic clocks show that the modern day is longer by about 1.7 milliseconds than a century ago. 1.7 milliseconds per century. That's nothing you would ever notice in a lifetime or in 10 lifetimes. But run the clock backward 4 billion years, and the numbers become startling. Early in Earth's history, shortly after its formation, A day may have been as short as 6 hours. Some models suggest it was even shorter immediately after the giant impact thought to have formed the moon. The young Earth was spinning more than 3 times faster than it spins today. What has been slowing it down? The moon. The moon's gravity pulls on Earth, creating tidal bulges, which generate friction and gradually transfer angular momentum from Earth's rotation to the moon's orbit. This process causes Earth's rotation to slow down. And as Earth's rotation slows, that angular momentum has to go somewhere. It goes into the moon's orbit. The moon, receiving this extra angular momentum, moves to a slightly higher orbit. It drifts outward. The moon continues to move away from Earth at a rate of about 4 centimeters per year. Its drift slowing as it goes. The moon is escaping, slowly, incrementally, in a process that will take billions of years to become significant, but escaping nonetheless, for centimeters per year. We know this with extraordinary precision because since 1969, scientists have been bouncing laser beams off reflectors left on the lunar surface by Apollo astronauts, measuring the distance to the moon with accuracy down to millimeters. The moon was once much closer. Its gravitational influence on early Earth was far stronger. The tides it raised would have been enormous. Walls of water crashing across coastlines with violence that is hard to imagine. And over billions of years, that gravitational conversation between Earth and Moon, that slow, continuous exchange of angular momentum, has shaped both worlds. It slowed the Earth, lengthened the day, and pushed the Moon outward to the relatively stable orbit we observe today. The Moon itself, meanwhile, has already reached the end point of this process. The same side of the Moon always faces Earth, because the Moon rotates exactly once each time it orbits our planet. This is called synchronous rotation, or tidal locking. The Moon's rotation was slowed by Earth's gravity until it matched the speed of its own orbit. At that point, the tidal bulge Earth was pulling on became permanently aligned. The friction stopped and the Moon locked. It now shows us the same face forever, or at least for as long as the Earth-Moon system continues in roughly its current configuration. All of the solar system's large moons are tidally locked with their planets. The bigger moons synchronize early in their existence, within hundreds of thousands of orbits. Tidal locking is an anomaly. It's the destination. It's what happens when two bodies share a gravitational relationship long enough. Angular momentum gets exchanged, rotation slows, and eventually the two bodies synchronize their spins and orbits. If you wait long enough, far longer than the current age of the universe, but still, Earth itself will become tidally locked to the Moon, one face of Earth permanently toward the Moon, one face permanently away. The day would be as long as the month. One side of the planet would be in perpetual daylight, the other in perpetual night. The universe is patient. It conserves its angular momentum, and it trades it slowly, steadily, across geological and astronomical timescales. Let's pull back now and look at the bigger picture, because the story of rotation doesn't end with planets and moons. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. The Milky Way moves through the local group of galaxies, which itself moves relative to the larger cosmic structure around it. At every scale, rotation is present. At every scale, things are spinning. And at every scale, the same principle applies. The angular momentum was always there, inherited from the structure above it, amplified by collapse, transferred through gravitational interaction, and carefully conserved. A useful way to think about it is this. The universe is not a place where things happen to be spinning. The universe is a place where stopping will require an explanation. Given the initial conditions of a universe filled with slightly uneven cloud of gas, and given the law of conservation of angular momentum, rotation is a natural, almost inevitable outcome. The absence of spin would be the surprising thing. Everything spins because everything was born from something that was already moving. The motion was inherited, amplified, and conserved. The universe has been bookkeeping since the very beginning. But wait, if rotation is simply inherited and conserved, then where did the original rotation come from? That question Where did the very first angular momentum in the universe come from is one we'll return to in the final part of this journey. It turns out it leads somewhere strange and genuinely uncertain, to questions about the Big Bang, the large-scale structure of the universe, and whether the cosmos itself might have a preferred direction of spin. For now, let's close this first act with a simpler thought. You are lying still. The room is quiet. Nothing moves. But you are standing on a planet that has been spinning for 4.5 billion years. A spin that came from a cloud of gas, a cloud that was itself barely rotating, so slightly and gently that no instrument of the time could have measured it. And yet that whisper of motion, that ghost of rotation, was enough, because in this universe, nothing is lost, especially not motion. The Earth spins, and it will keep spinning a little slower every million years, for billions of years to come. And when it's done, when the tidal forces have finally done their work across geological eternities, and Earth and Moon have settled into their final embrace, even then, the angular momentum won't be gone. It will be somewhere else. We've met the law already, in the skater, in the collapsing cloud, in the moon drifting outward from the Earth. But I want to go deeper now, because conservation of angular momentum isn't just a law that describes rotation. It's a window into something profoundly elegant about the architecture of the universe. Let's start with a question that seems simple, but isn't. Why is there a law of conservation of angular momentum at all? Why should the universe care about preserving rotation? Why doesn't it just let things spin up and spin down freely, in whatever way seems convenient? The answer lies in a piece of mathematics, so beautiful that physicists still talk about it with a kind of reverence. It comes from a theorem proved in 1915 by Emmy Noether, a German mathematician who, despite being one of the most brilliant minds in the history of her field, spent much of her career unable to hold a formal academic position because of her gender. Noether's theorem states, in essence, this: every continuous symmetry of the laws of physics corresponds to a conserved quantity. If the laws of physics are the same today as they were yesterday, if they don't change with time, then energy is conserved. That's where the conservation of energy comes from. If the laws of physics are the same here as they are 1,000 miles away, if they don't care about position in space, then linear momentum is conserved. And if the laws of physics are the same in every direction, if you can rotate your laboratory 90 degrees and the fundamental laws still hold, then angular momentum is conserved. The universe conserves rotation because it has no preferred direction. There is no special axis, no cosmically privileged orientation. Space is rotationally symmetric, and angular momentum is a conserved quantity that follows from that symmetry. This is one of the most remarkable things in all of science. The reason a spinning ice skater speeds up when she pulls her arms in, the reason the Earth keeps spinning after 4.5 billion years, is ultimately because the laws of physics look the same in all directions. The skater's spin is, in a sense, a proof that the universe has no preferred axis. Abstract? Yes, but true. Now let's see this law at work in some of the most dramatic settings in the universe. Take a neutron star. A neutron star is what remains after a massive star, one perhaps 8 to 20 times the mass of our sun, reaches the end of its life and undergoes a catastrophic explosion known as a supernova. The outer layers of the star are blasted into space. The inner core collapses. Before the collapse, the star's core might be roughly the size of Earth, 1,000 kilometers across, and rotating as many stars do, perhaps once every few days or even more slowly. After the collapse, the core has been compressed by gravity into a ball roughly 20 kilometers across. That's the size of a medium-sized city. A sphere of matter so dense that a teaspoon of it would weigh billions of tons. Matter so compressed that protons and electrons have been forced together to form neutrons, and the entire object is essentially one enormous atomic nucleus. And now, conservation of angular momentum. The radius has gone from thousands of kilometers to 20 kilometers. The moment of inertia has plummeted by an enormous factor. And because angular momentum is conserved, because the product of moment of inertia and spin rate cannot change unless something external acts on the system The spin rate must increase by that same enormous factor. The result: as a cloud collapses down to form a star, or in this extreme case a neutron star, there's an effect called conservation of angular momentum, which means that spin is accelerated as the object gets smaller. Some neutron stars rotate hundreds of times per second. There are known neutron stars, called millisecond pulsars, that complete more than 700 rotations per second. The surface of such an object is moving at a significant fraction of the speed of light, 700 times per second. That number should stop you cold. A solid object, an object more massive than the sun, packed into a ball 20 kilometers wide, spinning 700 times per second, not 700 times per minute, per second. And this came from a star that was probably rotating relatively slowly. All of that spin came from the collapse, from the shrinking of the radius, and the conservation of angular momentum. The law that explains why the figure skater spins faster also explains why neutron stars are the fastest spinning solid objects in the observable universe. Let's go in the other direction now, from the very large to the very small, because conservation of angular momentum doesn't just apply to cosmic objects. It applies to everything, including the fundamental particles that make up matter itself. Electrons, protons, neutrons, the basic building blocks of atoms, all possess a property called spin. Not spin in the everyday sense of something physically rotating, but an intrinsic angular momentum built into the particle at the quantum level. It's a property as fundamental as mass or charge. Electrons have a spin of 1/2, meaning their intrinsic angular momentum is a fixed, quantized value that cannot be changed. It cannot be added to or taken away. It simply is. This quantum spin is not the same as classical rotation. An electron is not, as far as we can tell, a tiny ball spinning on an axis in the usual sense. Quantum spin is something weirder and more abstract, but it is still angular momentum in the mathematical sense, and it is still conserved. When particles interact, when they collide, when they decay, when they combine to form atoms, the total angular momentum of the system before and after the interaction must be the same. Quantum spin plays into this accounting. Certain interactions are forbidden by the conservation of angular momentum alone. They simply cannot happen because they would require angular momentum to appear or disappear. So the same law that governs the spin of galaxies also dictates the interactions of the smallest known particles of matter. The universe applies the same rule at every scale. From a millisecond pulsar to an electron, from the orbit of Jupiter to the quantum mechanics of light. There is one law and it does not bend. Now, there's something I want to acknowledge here, because intellectual honesty requires it. The law of conservation of angular momentum is extraordinarily well established, but it applies in its pure form to isolated systems. A system where no external torque is acting. In the real universe, perfectly isolated systems are rare. Things interact. Gravity reaches across vast distances. Tidal forces exchange angular momentum between bodies. This doesn't break the law. It means the law applies to the total system, including everything that's interacting. Earth's rotation is slowing, but that angular momentum isn't disappearing. It's being transferred to the moon's orbit. The total angular momentum of the Earth-Moon system is conserved. Add in the sun, and the angular momentum of the entire solar system is conserved. Zoom out further, and the same is true. The universe as a whole conserves angular momentum. It trades, it shuffles, it transforms it from spinning objects to orbital motion to the intrinsic spin of particles, but it never creates or destroys it. At least, that is what our best physical understanding tells us. And there are no known violations of this principle. None. In every experiment ever conducted, every astronomical observation ever made, every particle interaction ever measured, angular momentum has been conserved. It is one of the most reliable facts we know about the universe. There's one more thing I want to say in this act, before we move on to how these principles play out on the grand stage of star and planet formation. Angular momentum has a direction. It's not just a quantity, a number that says this much rotation. It's a vector. It has a direction, and that direction is defined by the axis around which the rotation happens. By convention, if you curl the fingers of your right hand in the direction of rotation, your thumb points in the direction of the angular momentum vector. Earth rotates counterclockwise when viewed from above the North Pole, so Earth's angular momentum vector points, roughly, toward the North Star. This direction matters. When angular momentum is transferred from one body to another, through gravity, through tidal forces, through collisions, the direction matters. You can't just exchange amounts of spin. You exchange spin in particular directions. The orientation of the angular momentum vector carries information about the history of the system. This is why the solar system is so flat. The gas cloud that collapsed to form the sun and planets had a net angular momentum pointing in one direction. As everything collapsed and spun up and formed a disk, all of that material naturally settled into rotation around the same axis, the axis defined by the original angular momentum vector cloud. The disk formed perpendicular to that axis. The planets formed in the disk. And so every major planet in the solar system orbits the sun in very nearly the same plane, all going the same direction. It's not a coincidence. It's a memory. The flat solar system is the shape of an ancient spin. But not everything in the solar system follows this neat picture. There are exceptions. Planets that spin the wrong way or spin on their sides, or barely spin at all. And those exceptions are some of the most fascinating stories in planetary science. That's where we're going in part 2. We've learned why rotation exists, where it comes from, and what law governs it. In the next part of this journey, we'll watch the process unfold in real time. The birth of a star, the formation of worlds from a disk of swirling material, and then we'll look at the places where the universe broke its own patterns, and what those breaks tell us about the violence and chaos of the early solar system. Sleep well, and remember, you're spinning. There's a place in the constellation Taurus, the bull, roughly 450 light years from where you're lying right now, where astronomers have been watching something extraordinary, a star being born. The star is called H.L. Tauri. It's young by stellar standards, less than 1 million years old, which is a very brief moment in cosmic time, given that our own sun has been burning for 4.5 billion years. H.L. Tauri hasn't fully settled into the stable, hydrogen-fusing life of a mature star yet. It's still surrounded by the disk of gas and dust that formed alongside it, still embedded in the remnants of its birth cloud. In 2014, the ALMA telescope, the Atacama Large Millimeter Array, a collection of 66 radio antennas arranged across the high-altitude Atacama Desert in Chile, pointed at H.L. Tauri and took a picture. The image that came back stopped astronomers in their tracks. It showed a flat, circular disk of material surrounding the young star, beautifully symmetrical, and carved through a series of concentric rings and gaps, like the grooves on an enormous vinyl record. Dark rings alternating with bright ones, perfectly circular, centered on the star. Ever since ALMA captured that striking image of H.L. Tau, revealing intricate rings and gaps in the disk around a newborn star, astronomers have sought to understand how such complex structures could emerge so early. The gaps, scientists believe, are where planets are forming. A young planet sweeps through the disk in its orbit, clearing the material out of its path the way a finger drawn through sand leaves a groove. The bright rings between the gaps are the places where that material piles up, compressed and concentrated. Gaps indicate the presence of giant planets, which can form within approximately 1 million years, or less at significant distances from their host stars. 1 million years. The disk around H.L. Tauri is less than 1 million years old, and it already shows these structures. Planet formation, it turns out, begins almost immediately, before the star has even fully settled into its life. The solar system you live in, with its 8 planets arranged in their orderly orbits, began forming in a disk very much like this one, around a star very much like the one at the center of H.L. Tauri system. And all of it, the disk, the rings, the orbits, the fact that the planets move in the same plane and in the same direction, traces back to the rotation that was built into the collapsing cloud from the very beginning. Let's walk through that process carefully. because it's one of the most elegant stories in all of science. A molecular cloud begins to collapse. We covered the basics of this in part 1, but now I want to go deeper into the details of what actually happens as that cloud pulls itself together under gravity and how rotation shapes every stage of the process. The cloud starts large, enormous. Protoplanetary disks can have sizes up to roughly 1,000 astronomical units, where 1 astronomical unit is the average distance between Earth and the Sun. The cloud from which a solar system forms is vastly larger than the disk it eventually produces. We're talking about structures that start out spanning distances measured in light years and end up compressed into a disk measured in hundreds of astronomical units. That's a compression by a factor of tens of thousands. And throughout that compression, as the cloud shrinks and heats and spins faster, the rotation is doing something crucial. It's sorting. Remember, when the cloud collapses, material falling along the rotation axis, from above and below, can fall straight and toward the center, pulled directly by gravity. There's nothing stopping it, but material that's falling inward in the plane of rotation faces an additional force, the centrifugal effect of spin, which pushes it outward. Gravity pulls in, rotation pushes out. For material in the plane of rotation, these forces fight each other. The result: material along the spin axis can collapse onto the forming star, but material in the spin plane has its infall halted by the centripetal force generated by the rotation. A disk is formed. The cloud flattens. What began as a roughly spherical blob of gas and dust becomes, over tens of thousands of years, a flat rotating disk with dense, hot center, the forming star, and a broad, thin plane of material extending outward. This disk is called a protoplanetary disk, and it is remarkable. Protoplanetary disks are made of roughly 99% gas and 1% dust by mass. That 1% dust doesn't sound like much, but it's the dust, the tiny solid grains of rock, ice, and carbon compounds that eventually becomes everything solid in the solar system. The planets, the moons, the asteroids, the comets. Every mountain and ocean and piece of metal in the world you live on was once a speck of dust circling a young star in a flat, spinning disk. The gas, mostly hydrogen and helium, eventually gets blown away by the star's radiation and stellar winds. But before that happens, the disk is a dynamic, churning environment where collision, sticking, and gravity are building worlds out of almost nothing. The process of building planets from that dust is called accretion, and it happens in stages. It begins at the smallest scale imaginable. Individual dust grains, floating in the disk, occasionally drifting into each other and sticking together. Static electricity plays a role in these early collisions. The same force that makes a balloon stick to a wall after you rub it on your hair. Grains stick to grains, and over time, collections of grains form larger aggregates. Pebbles, rocks, chunks. Then gravity begins to take over. Chondrules glommed onto other chondrules and stuck themselves together into primordial rocks, building up larger and larger objects. Eventually, these objects got to be big enough to pull their mass into a round shape. We call them planetesimals. Planetesimals gobbled up nearby asteroids and smashed into other planetesimals, merging and growing through time through the process of accretion. Once a planetesimal gets large enough, its gravity is strong enough to attract material from further away. A runaway process begins. The larger you are, the more you attract. The more you attract, the larger you become. A handful of these growing bodies come to dominate their region of the disk, eventually sweeping their orbital zones clean of smaller material. And throughout all of this, the grain sticking, the pebble collisions, the planetesimal mergers, the disk keeps spinning. Every object inherits the rotation of the disk. Every orbit goes in the same direction. Every body forms in the same plane. A sun-like star usually takes approximately 1 million years to form, with a protoplanetary disk evolving into a planetary system over the next 10 to 100 million years. 10 to 100 million years. That's the timescale on which worlds are made. It sounds long from human perspective, but in cosmic terms it's quite fast. a small fraction of a star's total lifetime. Now, there are two competing models for how the larger planets, the gas giants like Jupiter and Saturn, came to be, and I want to be clear that both have scientific support, and neither is considered definitively proven to the exclusion of the other. The first model is called core accretion. In this picture, a solid rocky core forms first through the collision and merging of planetesimals. Just as we described, when that core reaches a critical mass, roughly 10 times the mass of Earth, its gravity becomes strong enough to pull in large quantities of gas from the surrounding disk. The gas piles onto the solid core, and a gas giant is born. The second model is called gravitational instability. In this picture, the disk itself, the whole gas and dust disk, becomes locally unstable in certain regions and collapses directly, in a matter of thousands of years, into a clump of gas that eventually becomes a giant planet. No rocky core required. Both of these scenarios have had success in predicting and explaining observed properties of exoplanet systems, but neither provides complete picture of planet formation. Each scenario has major shortcomings which are still yet to be resolved. This is important to say plainly. We do not have a definitive, settled theory of exactly how gas giants form. Core accretion is more widely favored among planetary scientists for the formation of our own solar systems, Jupiter and Saturn. The evidence from meteorites and models leans in that direction, but gravitational instability may be more relevant in other systems, particularly those with very massive planets on wide orbits. The full picture almost certainly involves both processes operating in different conditions. What we do know, regardless of which model applies, is that rotation runs through all of it. The disk spins, the material orbits, the forming planets inherit that orbital motion, and the whole system settles into flat, orderly arrangement we see. Here's something that brings the story into sharp, modern focus. We can actually watch this happen, not in our own solar system, which finished forming billions of years ago, but in other systems right now, with the right instruments. Recent ALMA observations captured high-resolution images of protoplanetary disks in extreme environments and found evidence of gaps and rings in most of them, structures commonly associated with the formation of giant planets. In 2014, that landmark image of H.L. Tauri showed rings and gaps in a disk less than 1 million years old. The scientific community was surprised. The conventional expectation had been that planets took much longer to begin forming. Recent ALMA observations have revealed that many protoplanetary disks have substructures such as gaps and rings. This is strong evidence that planets are forming and sweeping up material from the disk. Many protoplanetary disks show such signs, suggesting that planet formation is already in progress or is almost completed in the systems we typically refer to as protoplanetary disks. In other words, planet formation isn't rare and it isn't slow. It appears to begin almost as soon as the disk forms, and the signatures of forming planets, those rings and gaps, are present in a large fraction of the young disk systems we observe. The universe seems to be quite productive when it comes to making planets. In 2018, the disk substructures, a high-angular resolution project, known as JARP, showed that rings and gaps are widespread in most protoplanetary disks. The universe is not building solar systems as rare exceptions. It appears to be building them constantly, everywhere stars form, which means everywhere you look in the sky, in any direction, the flat spinning disks are there, and the planets are assembling inside them, inheriting the rotation of the original cloud, continuing the cycle that has been going on since the first stars ignited in the early universe. Let's come back to our own solar system for a moment, and notice something that the whole story of disk formation explains remarkably well. The planets in our solar system orbit the sun in almost exactly the same plane, a flat sheet of orbits that astronomers call ecliptic. They all go around the sun in the same direction, counterclockwise when viewed from above Earth's North Pole. Most of them also spin on their axes in the same direction as they orbit. All of this is exactly what the nebular model predicts. The flat solar system is a fossil of the original disk. The shared direction of orbital motion is a memory of the disk's rotation. The spins of the planets, to the extent they align with their orbital motion, reflect the rotation of the material they formed from. And now we come to something equally important, the places where this pattern breaks down. Because not everything in the solar system fits the tidy picture. There are planets that spin the wrong way. There are planets tilted at impossible angles. There are moons that orbit backward. And these exceptions are not embarrassments of theory. They are, in fact, one of the most revealing things about the violent and chaotic history of the early solar system. The exceptions tell the story of the collisions. The early solar system was not the orderly, peaceful arrangement of planets we see today. It was a demolition derby. In the first 100 million years after the sun ignited, the solar system was full of debris, countless rocky bodies, protoplanets, icy planetesimals, leftover material from the disk that hadn't yet been swept up by the forming planets. These objects were all moving in orbits, and orbits can cross. And when orbits cross, things collide. The collisions of the early solar system were not gentle. They were tremendous impacts, objects the size of small planets slamming into each other at tens of kilometers per second, releasing energy equivalent to billions of nuclear weapons in single events. These collisions reshaped worlds. They melted surfaces, stripped atmospheres, and, most relevant to our story, they changed rotation. When a large object strikes a planet at an angle, it delivers a torque. It imparts angular momentum to the planet in a direction that may be completely different from the planet's original spin. A big enough impact, hitting at the right angle, can tilt a planet sideways. It can reverse its rotation entirely. It can knock it over. And the evidence for exactly this kind of violence is written into the rotations and tilts of the planets themselves. Start with Uranus. Uranus is the seventh planet from the Sun. It's an ice giant, a world roughly 4 times the diameter of Earth, composed largely of water, methane, and ammonia in a dense, hot, high-pressure interior beneath an atmosphere of hydrogen and helium. In many ways, it's a fascinating world. But the first thing any astronomer notices about Uranus is the thing that makes it unlike anything else in the solar system. It is tipped over. Uranus possesses an extreme axial tilt of approximately 97.77 degrees. This near 98-degree tilt means the planet's rotational axis is almost parallel to the plane of the solar system, giving it the nickname of the sideways planet. Think about what this means physically. Earth's axis is tilted about 23.5 degrees from vertical. That's what gives us our seasons. Uranus is tilted nearly 98 degrees. Its axis of rotation lies almost in the plane of its orbit. Uranus doesn't spin upright like a top. It rolls, like a ball rolling along its orbital path. Its north pole points sideways. For part of its 84-year orbit, one pole is in constant daylight for decades, while the other is in constant darkness. Seasons so extreme they have no counterpart anywhere else in the solar system. How did this happen? The most widely accepted theory for Uranus's axial tilt is the giant impact hypothesis. This theory suggests that early in the solar system's history, a massive object collided with Uranus, causing the planet's tilt. A Mars-sized object struck Uranus with enough force to alter its rotation axis. But the story is more complicated than a single impact. And this is where the science becomes genuinely unsettled, and where scientific honesty requires acknowledging that multiple hypotheses exist and no single one has been confirmed. In simulations, a single giant impact could produce the correct tilt, but it came with an important caveat. The moons orbited in the wrong direction, counter to Uranus's rotation. The moons of Uranus are actually prograde. They orbit in the same direction as the planet rotates. The only way for Uranus to have kept its moons in the right place and moving in the right direction was to have suffered multiple giant impacts. If we are right, Uranus was hit at least twice by big objects about the mass of the Earth, researcher Morbidelli concluded. He noted that Neptune's tilt, though only about 1/3 that of Uranus, is also best explained by a giant impact. But not everyone is convinced that giant impacts tell the whole story. A third hypothesis suggests that Uranus's tilt was not caused by impacts, but rather by gravitational perturbations from an unknown early planet that was later ejected from the solar system. Simulations of early solar system instability show that many early planetary bodies may have existed temporarily before being ejected. A temporary gravitational resonance between Uranus and another large planetary body could have caused a slow, progressive axial shift rather than a sudden impact. The honest summary: the giant impact scenario is the leading hypothesis for Uranus's tilt, and it is supported by computer simulations. But no single version of it, one impact, two impacts, which direction, which size, has been confirmed. And alternative mechanisms, including gravitational resonances, have not been ruled out. We do not know with certainty exactly what happened to Uranus. What we do know is that something violent happened. Something that took a planet that should have been spinning upright, like the rest of the solar system, and knocked it onto its side. And then there's Venus. Venus is in many ways Earth's twin. It's nearly the same size as Earth, about 95% of Earth's diameter. It's the closest planet to us. It's rocky with a solid surface. From the outside, in terms of size and composition, Venus and Earth are remarkably similar. But Venus spins in the wrong direction. Every planet in the solar system, every single one, formed in a disk that was rotating in a particular direction, and the vast majority of them still spin in that same direction. We call it prograde rotation. The spin matches the orbital direction. Earth spins prograde. Mars spins prograde. Jupiter, Saturn, Neptune, all prograde. Venus is a prime example of retrograde rotation. It spins clockwise, opposite to its orbital path. And it doesn't just spin backward, it spins with extraordinary slowness. Venus has an exceptionally slow rotational period, 243 Earth days, longer than its 224.7-day year. Read that again. Venus's day is longer than its year. It takes Venus longer to complete one rotation on its axis than it does to orbit the Sun. If you stood on the surface of Venus, which you couldn't, because the surface temperature is around 465 degrees Celsius and the atmospheric pressure would crush you, but if you could, the sun would rise in the west and set in the east, moving so slowly that you would age noticeably before it moved perceptibly across the sky. How did this happen? Here, again, we have competing hypotheses, none of which has been confirmed as a definitive explanation. One leading hypothesis is that an early giant impact flipped Venus over. In this scenario, a Mars-sized body collided with young Venus, changing its spin direction and slowing it to the current rate. However, scientists emphasize that no single explanation has been confirmed, and the cause of Venus's retrograde spin remains a mystery. The second theory involves tidal forces from Venus's thick atmosphere. Gravitational and thermal tides between the Sun and Venus's dense atmosphere could have gradually slowed Venus's spin over billions of years, eventually bringing it to its current crawl. This mechanism works, but only if Venus started with a rotation period somewhere between half a day and 3 days. Most scientists believe Venus's retrograde rotation likely resulted from a combination of impacts, tidal forces, and atmospheric effects rather than a single cause. And there's an additional layer of mystery. Recent data from ESA's Venus Express and NASA's Magellan missions indicate that Venus's rotation rate is not constant, but fluctuates slightly over time. The length of Venus's day appears to have changed by several minutes between observations taken years apart. The reason for this variation is not fully understood. Critics of the collision impact hypothesis point out that an asteroid big enough to reverse Venus's rotation would also have been strong enough to destroy the planet itself. This argument has been contested by modeling studies that show it's possible to reverse a planet's spin without destroying it, if the impact geometry is right, but it illustrates the genuine difficulty of the problem. Venus's backward spin is one of the most interesting unsolved problems in planetary science. We know the outcome. We don't know the cause, and the data required to definitively resolve it. Detailed knowledge of Venus's early rotation and interior structure is extremely difficult to obtain. Uranus and Venus represent two different kinds of exception to the solar system's general pattern of rotation, but they are not the only exceptions. Pluto, though no longer classified as a planet, still one of the most interesting objects in the outer solar system, has an axial tilt of about 122 degrees, making it like Uranus, technically retrograde in its rotation. This is thought to be related to its complex tidal relationship with its large moon, Charon, which is so massive relative to Pluto that the two bodies are mutually tidally locked, both showing the same face to each other, orbiting a center of mass that lies between them rather than inside Pluto. Then there are the exoplanets. Since the 1990s, astronomers have discovered thousands of planetary systems around other stars. And one of the most striking findings of this search has been how disordered many of these systems are. Astronomers have found that a significant fraction of hot Jupiters, giant planets orbiting very close to their host stars, move on orbits substantially misaligned with the rotation axis of their host star. Contemporary models of planetary formation produce planets on nearly coplanar orbits with respect to their host star's equator. In other words, the theory predicts that planets should form in a flat disk aligned with their star's equator. And many planets do. But a large fraction of the most massive planets we've found are tilted, some dramatically so. Some orbit at right angles to their star's equator. Some orbit in the opposite direction entirely. A significant fraction of hot Jupiters are observed to have large stellar obliquities. Their orbital angular momentum is often misaligned with the spin axis of their host stars. How did this happen? Again, we have hypotheses rather than certainty. One leading explanation involves the causative mechanism, a gravitational interaction that can occur when a massive third body, another planet, or a distant companion star, perturbs the orbit of a closer planet, causing it to tilt and become more eccentric over time. Another explanation involves chaotic scattering. Giant planets flinging each other into new orbits through close gravitational encounters in the early chaos of a young system. The emerging picture from exoplanet science is that our solar system, with its orderly, coplanar, prograde rotating planets, may actually be somewhat unusual. Many planetary systems are Messier. They carry the scars of more violent histories. The collisions and gravitational interactions of the early solar system were more restrained in our case than in many others. Or perhaps we were just lucky. The exceptions: Uranus tipped on its side, Venus spinning backward, exoplanets in wildly misaligned orbits, are not embarrassments to the theory of how rotation originates. They are confirmations of it, in a deeper sense. The theory says, planets form in a rotating disk, inheriting the disk's angular momentum. But the early solar system is chaotic, and collisions can alter the angular momentum of individual bodies. The exceptions are exactly what you'd expect from a universe where rotation is the default, but where violent impacts can override the default in individual cases. The rule is rotation. The exceptions are violence. And the scale of that violence, written in the tilted axis of Uranus and the backward spin of Venus, should give us pause. These weren't small perturbations. These were planet-sized objects colliding with planet-sized objects at tens of kilometers per second. Events of almost incomprehensible energy, reshaping worlds in the span of hours. The Earth was not immune to this violence. The giant impact that most planetary scientists believe formed the Moon, a collision between the early Earth and a body roughly the size of Mars, called Theia approximately 4.5 billion years ago, almost certainly altered Earth's rotation as well. Before that impact, the early Earth may have had a very different day length, a different axial tilt. The Earth we live on is, in part, the product of a catastrophic collision. We are the survivors of a demolition derby. And our rotation, our 24-hour day, our 23.5-degree tilt, our seasons, is a result not just of the orderly physics of disk formation, but of the specific, particular chaos of our solar system's early history. There is something worth sitting with here. The rotation of the Earth, the thing that gives us day and night, that structures our entire experience of time, that has shaped the biology of every living thing on this planet, is not simply a clean consequence of physics. It is partly an accident, a historical contingency, the result of a specific collision that happened in a specific way at a specific moment 4.5 billion years ago. Had Theia struck at a slightly different angle, The Earth might rotate faster or slower. Its tilt might be different. The seasons as we know them might not exist. The length of the day might have been different, and the evolution of life on this planet. Every organism that has ever lived timed its biology to the rhythm of the rotating Earth might have gone in a completely different direction. The spinning of the world you live on is a combination of universal physics and local accident. It is at once one of the most predictable consequences of star formation and one of the most historically contingent facts about this particular planet. Both things are true. Let's close part 2 here and take stock of what we've learned. We've watched the birth of the solar system, the collapse of a cloud, the formation of a disk, the slow accretion of dust into rocks and rocks into worlds. We've seen how rotation is built into every stage of that process, how the flat solar system is the shape of an ancient spin. And we've seen the exceptions, the tilted, the backward, the misaligned, and understood them as the marks of violence written into the rotation records of individual worlds. In part 3, we go bigger. We leave the solar system behind. We leave individual stars and planets behind. We go to the scale of galaxies, structures containing hundreds of billions of stars, and ask, where did their rotation come from? And then we ask the question that sits at the very edge of what physics can currently answer. Does the universe itself rotate? That question has a remarkable history and a genuinely uncertain answer. And it is where this journey ends. Step back from the solar system. Step back from individual stars and their disks. Step back until the sun is just one light point among 100 billion others, until the Milky Way is a flat, glowing spiral hanging in the dark. And now ask the question again. Why does this spin? The Milky Way is rotating. The sun, along with everything near it, orbits the galactic center at roughly 500,000 miles per hour. It completes one orbit every 225 million years. The stars in the inner regions of the galaxy orbit faster. The stars in the outer regions orbit more slowly. The whole structure, a disk roughly 100,000 light years across, containing somewhere between 100 billion and 400 billion stars, is in continuous rotation. And it is not alone. Look outward through any large telescope, and you'll find that the majority of galaxies are disk-shaped and rotating. Spiral galaxies like the Milky Way, like Andromeda, like the hundreds of billions of other spiral galaxies visible in the observable universe. They all spin. The rotation of galaxies is not an exception. It is a rule. So where did it come from? For planets and stars, we had a clear answer. The rotation was inherited from a collapsing cloud of gas and amplified by conservation of angular momentum as that cloud shrank. The process was well understood. The physics was clean. For galaxies, the story is more complicated and, in some ways, more beautiful, because galaxies didn't form from a single collapsing cloud. They formed from the large-scale structure of the universe itself. And to understand how they got their spin, we need to look at the environment they were born in. The theory that explains the origin of galactic rotation is called tidal torque theory. It was developed over decades with foundational contributions from Fred Hoyle in 1949, P.J. Peebles in 1969, and Stephen White in 1984. It remains the standard framework for understanding why galaxies rotate. Here is the basic picture. In the early universe, matter was not perfectly smooth. Immediately after the Big Bang, the universe was an almost featureless sea of hot plasma. But almost featureless is not the same as perfectly featureless. There were tiny fluctuations in density. Some regions were slightly denser than average. Some were slightly emptier. These fluctuations were small, variations of only about 1 part in 100,000. But gravity amplifies small differences over time, and those tiny fluctuations were the seeds of everything that exists today. Over hundreds of millions of years, the denser regions attracted matter from their surroundings. They grew. They eventually collapsed into dark matter halos, vast, roughly spherical clouds of matter held together by gravity. And within those halos, the ordinary matter, gas, dust, eventually stars, condensed further into what we now call galaxies. This process of halo formation is where the spin comes in. The key insight of tidal torque theory is this. A collapsing region of the early universe is not a sphere floating in empty space. It is surrounded by neighboring overdensities. Other regions are also collapsing or will collapse or are in the process of doing so. These neighboring structures are all pulling gravitationally on each other. And because they are not perfectly symmetric, because the collapsing region is not exactly spherical and the surrounding matter distribution is not exactly uniform, these gravitational pulls create a torque. In tidal torque theory, the angular momentum of dark matter halos arises from the tidal torque suffered by aspherical collapsing patches due to surrounding mass fluctuations. Think of it this way. Imagine a somewhat elongated cloud of matter collapsing under gravity. To its left, another large concentration of matter is pulling on it. To its right, a different concentration is pulling from another direction. These two forces are not perfectly opposing. They're slightly offset. The net effect is a twist, a torque, and a torque applied to a system produces angular momentum. Until the initial density perturbations in the universe reach maximum expansion, turnaround, their angular momentum grows linearly with cosmic time as a consequence of the torques exerted by the tidal gravitational fields from neighboring overdensities. After turnaround, structures decouple from the Hubble flow and these overdensities collapse and virialize, conserving angular momentum in the process, such that the angular momentum of individual halos may be predicted within an order of magnitude by the initial large-scale gravitational tidal torques before maximum expansion. It's a subtle and important sequence. The angular momentum is built up gradually, while the proto-galaxy is still expanding, still in the early phase before it turns around and begins collapsing. Once collapse begins and the system detaches from the general expansion of the universe, it holds on to that accumulated angular momentum and carries it inward. By the time the galaxy is formed, it is already spinning. Not because something hit it, not because it collapsed from a single rotating cloud, but because the gravitational environment it was born in was slightly asymmetric. The spin of a galaxy is the memory of an uneven neighborhood. Now, there is an important complication in this story, and it involves dark matter. Dark matter is a name given to a form of matter that does not interact with light in any known way. It neither emits, absorbs, nor reflects electromagnetic radiation, but which does have gravity, and which appears to make up approximately 85% of all the matter in the universe. We know it exists because of its gravitational effects. Galaxies rotate faster than they should if they only contain the visible matter we can see. Galaxy clusters bend light in ways that require more mass than is visible, and the large-scale structure of the universe matches simulations only if most of the matter is dark. Dark matter does not form stars or planets. It does not collapse into disks. It forms large, diffuse halos, extended spherical structures that surround and dwarf the visible parts of galaxies. Every galaxy we know of is embedded in a much larger halo of dark matter, and this has direct consequences for how galaxies spin. Dark matter halos are spun up by tidal torques originating from large-scale structures, resulting in an average spin parameter, a dimensionless measure of halo angular momentum, of approximately 0.04. That number, 0.04, is a spin parameter, a dimensionless measure of how much angular momentum a halo has relative to how much it would need to be rotationally supported, like a spinning top that holds its shape through rotation. A value of 0.04 is modest. Dark matter halos are not spinning fast. They are slowly, lazily rotating, far from the tight, flat disks of visible galaxies. The visible part of a galaxy, the stars, gas, and dust that make up the disk, forms inside the dark matter halo. As the gas falls inward under gravity, it is denser and more compact than the dark matter, and it dissipates energy through radiation. When gas loses energy but conserves angular momentum, it settles into a flat rotating disk. The same physics we saw in protoplanetary disk formation, now operating at the scale of a galaxy. The dark matter halo provides a gravitational scaffolding. The gas inside it, falling inward and conserving angular momentum, forms the spinning disk. this picture is not complete. There are ongoing questions about exactly how the angular momentum is transferred between the dark matter halo and the visible galaxy, and whether galaxies end up with more or less angular momentum than their host halos. Simulations have made substantial progress here, but the details of how angular momentum moves through a galaxy during its formation and evolution are still an active area of research. What is well established is the following. The origin of galactic spin lies in the gravitational torques of the cosmic web, the vast network of filaments, sheets, and voids that forms the large-scale structure of the universe. Galaxies spin because they were born in an uneven universe, where neighboring concentrations of matter provided the twist. The rest is conservation of angular momentum. In 2025, the first robust observational confirmation of tidal torque theory was reported, using the gas component of central massive elliptical galaxies, whose angular momenta respond sensitively to external torques. By comparing observed gas angular momentum vectors with those predicted from the primordial density field reconstructed for the nearby universe, researchers detected a strong directional correlation with a significance of about 7 sigma, essentially confirming that the angular momentum direction a galaxy has today was imprinted by the gravitational tidal field of the early universe. The spin of galaxies is not random. It is connected, statistically, to the large-scale structure of the cosmos itself, and that connection has now been measured. There is something worth pausing on here. We've traced the origin of rotation from the spinning of the Earth to the collapse of protostellar clouds, to the tidal torques of the cosmic web. At every scale, the same principle applies. Rotation comes from somewhere. It is not spontaneous. It is generated by asymmetric forces acting on extended, non-spherical systems. And once generated, it is conserved. The universe is, in a sense, a hierarchy of spinning systems, each born from the gravitational environment of the level above it. Planets spin because disks spin. Disks spin because clouds spin. Clouds spin because of the tidal field of the galaxy. And galaxies spin because of the tidal field of the cosmic web. All the way down, or up, it's the same law, the same conservation, the same bookkeeping. But now comes a question that sits at the edge of this hierarchy. The question that even the physicists who spend their careers on this topic approach carefully. If everything we can see spins because of gravitational forces from its environment, what is the environment of the universe itself? In 1949, Kurt Gödel published a paper that made Einstein uncomfortable. Gödel was, at the time, already one of the most celebrated logicians of the 20th century, the man who had proved that any sufficiently powerful mathematical system contains true statements that cannot be proven within that system, a result so profound it changed the foundations of mathematics forever. But in 1949, Gödel turned his attention to physics, and specifically to a puzzle about time. He wanted to know whether the universe permitted travel into the past. Working within Einstein's general theory of relativity, the framework that describes gravity as the curvature of space-time, Gödel found an exact solution to Einstein's field equations that describe a universe filled with uniform, rotating fluid of matter. In this universe, matter rotates relative to what physicists call the compass of inertia, the background structure of space-time itself. Gödel's universe is infinite, non-expanding, and filled with an idealized, homogeneous, perfect fluid. It rotates to stay balanced against gravitational collapse. The angular velocity outward juxtaposed to the gravitational pull inward. And in this rotating universe, something extraordinary followed. The rotation of space-time created paths through space and time that loop back on themselves. Closed time-like curves, as physicists call them, paths along which a traveler, moving always forward in time from their own perspective, could return to their own past. Gödel demonstrated that it was possible for a time-like world line to return to its starting point in both space and time. This suggests that an object could, in principle, travel back to its own past. Gödel's point was not that time travel was practical. It was philosophical. He argued that if the laws of physics permit a universe in which the past is reachable, then time, in the objective, flowing sense that most people intuitively understand it, Time as a river that moves only forward may not be a fundamental feature of reality at all. It may be an artifact of our particular universe's geometry. Einstein read the paper and was deeply troubled. He wrote that Gödel's results showed a problem in the foundations of general relativity that he had not previously recognized. But here's the critical question for our story. Does our universe actually rotate? The answer, as of what we currently know, is not in the way Gödel described, and almost certainly not at any significant rate. But the question is more subtle than a simple no. The model of cosmology that best fits all current observations, the lambda CDM model, for lambda cold dark matter, assumes that the universe is isotropic and homogeneous on large scales. Isotropic means the same in every direction, no preferred axis, no preferred orientation. A universe that rotates whatever preferred axis, the axis of rotation, and that would show up as an anisotropy, a directional bias, in the universe's properties. In particular, it would imprint a detectable pattern on the cosmic microwave background, the faint afterglow of radiation left over from the early universe. In a comprehensive analysis of CMB data from the Planck satellite, researchers tested whether the expansion of the universe is isotropic using all degrees of freedom in anisotropic models. For the vector mode associated with vorticity, that is, rotation, they obtain a limit on the anisotropic expansion that is an order of magnitude tighter than previous results. Including all degrees of freedom simultaneously for the first time, anisotropic expansion of the universe was strongly disfavored, with odds of 121,000 to 1 against. To put that in concrete terms, Planck measurements place a stringent upper limit on cosmic rotation. The ratio of rotational velocity to expansion rate must be less than 7.6 times 10 to the minus 10. That is an extraordinarily small number. The universe, if it rotates at all, rotates so slowly that the effect is far below the threshold of current detection. This does not mean the question is settled. It means we have placed very tight limits on how fast the universe could be rotating, and those limits are consistent with zero. Zero is compatible with the data, but so is a rotation too small to detect. The absence of evidence is not the same as evidence of absence, though in this case, the limits are so tight that any remaining rotation would have essentially no observable consequence. Now, there is a separate and more recent line of investigation that is worth discussing carefully. The question of whether there is a preferred direction in the universe's structure independent of rotation per se. In 2011, physicist Michael Longo published a study examining the spin directions of spiral galaxies in the Sloan Digital Sky Survey. A study of 15,000 galaxies found that there was a small bias in the direction of rotation. Because of the relatively small sample size, the evidence was somewhat weak. Longo's finding was that slightly more galaxies appeared to spin counterclockwise than clockwise when viewed from a particular direction in the sky. He interpreted this as a possible hint of a large-scale asymmetry. This result attracted significant attention and spawned a decade of subsequent studies. Researcher Lior Shamir, in particular, has published numerous papers using progressively larger datasets, from SDSS to Pan-STARRS to the Hubble Space Telescope to the James Webb Space Telescope, arguing that the asymmetry is real, statistically significant, and consistent across multiple instruments and sky surveys. Asymmetry between the number of galaxies rotating clockwise and the number rotating counterclockwise has been observed in studies using Earth-based telescopes such as SDSS, Pan-STARRS, and DCAM, and also through observations made by space-based instruments, including the Hubble Space Telescope. However, this line of research is genuinely contested, and scientific honesty requires presenting both sides clearly. Another study by Patel and Desmond, 2024, suggested that the distribution of directions of galaxy rotation is random. Their work was based on data used in previous studies and applied a new statistical method. The debate concerns whether the standard binomial distribution statistics used in earlier papers or the new complex method proposed by Patel and Desmond is more appropriate for detecting such asymmetry. This is not a case where one side is clearly right and the other clearly wrong. It is an active scientific debate about methodology, statistical approaches, and how to properly account for systematic biases in galaxy classification. The asymmetry of real is small, a few percent, not a dramatic imbalance. Small signals are difficult to disentangle from systematic errors, and different statistical methods can give different answers when applied to the same data. What can be said with confidence is this: the standard model of cosmology predicts no preferred direction and no global rotation. The CMB data tightly constrain any such rotation to levels far below observability. Any claimed asymmetry in galaxy spin directions is currently the subject of active debate and has not been accepted by the broader cosmology community as established. The question of whether there is a subtle preferred direction in the structure of the universe remains genuinely open. It is a hypothesis held by a minority of researchers, contested by others, and not yet resolved by the data. And beneath all of this sits the most fundamental version of the question: where did angular momentum ultimately come from? If everything spins because angular momentum was transferred from something else, and that something else spins because it inherited angular momentum from the structure above it, and galaxies spin because of the tidal field of the cosmic web, where did the cosmic web get its angular momentum? The tidal torque theory provides a mechanism: tidal torques between neighboring overdensities. But this requires that those overdensities already be present and that they have, at minimum, some asymmetry. The asymmetry traces back to the quantum fluctuations of the very early universe. Tiny variations that were inflated to cosmic scales during a period of rapid expansion called inflation, becoming the seeds of all structure. But quantum fluctuations are random. They don't have a preferred spin direction. In the standard picture, the total angular momentum of the universe is zero. Every counterclockwise spin is balanced somewhere by a clockwise spin. The net is nothing. This is consistent with conservation laws applied to the universe as a whole. If the universe began in a state of zero angular momentum, which is one natural initial condition, then it must have zero angular momentum today, no matter how complex its internal structure has become. Whether this is actually the case, whether the total angular momentum of the observable universe is precisely zero, or whether some primordial imbalance introduced a net spin, is a question that current observations cannot definitively answer. It would require being able to observe far more of the universe than we can, or finding some observational signature that distinguishes zero from very nearly zero. We don't have that resolution. Not yet. So, does the universe rotate? The honest answer is that we don't see evidence that it does. The limits placed by CMB observations are extremely tight. The standard model, which does not include cosmic rotation, fits the data extraordinarily well. Any rotation that might exist is smaller than anything we could currently detect. Whether any small asymmetry in galaxy spin directions, if confirmed, would require a rotating universe or could be explained by other mechanisms. That question is open, and the debate is ongoing. What Gödel showed 76 years ago is that a rotating universe is mathematically permitted by general relativity. He did not claim it was our universe. He used it to make a point about time. The physics is valid. The universe he described simply does not appear, from all available evidence, to be the one we live in. But the door, as yet, has not been entirely closed. We've come a long way. We started with a figure skater on ice, pulling in her arms. We ended at the edge of the observable universe, asking whether the cosmos itself spins. Between those 2 points, we've watched stars be born from collapsing clouds. We've seen the solar system take shape in a flat disk of gas and dust. We've traced a violent early history of planets, the collisions that tipped Uranus sideways and sent Venus spinning backward. We've looked at galaxies and understood how they got their rotation from the gravitational torques of the cosmic web. We've stood at the boundary of what cosmology can currently say about whether the universe itself has a preferred direction. All of it, from the smallest scale to the largest, governed by the same principle: conservation of angular momentum. I want to take this last act to say something about what that principle means, not just as physics, but as a statement about the nature of the universe. There's a phrase I've been turning over throughout this journey. It came from thinking about what it means for a physical quantity to be conserved. We say angular momentum is conserved. What that actually means in practice is this: the universe keeps track. Every spin, every orbit, every rotation. It is recorded, not in any mystical sense, but in the most concrete physical sense possible. The angular momentum a system has right now is a direct consequence of every interaction that system has had, every torque that was applied to it, all the way back to its origin. Nothing is lost. Nothing is forgotten. The day you're living through, its length, its rhythm, the fact that the sun rises in the east and sets in the west, is the accumulated record of everything that has happened to the Earth since it formed. The giant impact that made the moon, the slow tidal exchange of the moon over billions of years, the ancient collision that gave the Earth its axial tilt. Every one of those events left a permanent mark in the rotation of this planet, and that mark persists today and will persist for billions of years to come. When you watch the sun set, you are, in a sense, reading history. There's a concept in physics called the arrow of time, the direction in which time flows from past to future. Many of the fundamental laws of physics are symmetric in time. They would work the same way if you ran them backward. A particle interacting with another particle looks the same forward and backward, mathematically. But the large-scale behavior systems, the way entropy increases, the way hot things cool and cool things don't spontaneously heat up, defines preferred direction in time. Angular momentum is interesting in this context because it is both deeply conservative and deeply historical. It doesn't increase like entropy. It doesn't have a preferred direction in time. An isolated spinning system spins in the same direction, at the same rate, regardless of which way time is running. But in the real universe, where systems are never truly isolated, where tidal forces slowly exchange angular momentum between bodies, the rotation of any given object carries within the accumulated history of all those exchanges. The moon's tidal locking is a record of billions of years of tidal friction. The length of the Earth's day is a record of all the angular momentum that has been transferred away to the moon. The orbit of Venus, spinning backward and impossibly slowly, is a record of some catastrophic collision in the ancient past. Every rotation is a fossil. Emmy Noether showed us that angular momentum is conserved because of rotational symmetry, because the laws of physics are the same in all directions, because space has no preferred axis. That symmetry is one of the most profound features of the universe as we know it. It means that wherever you are in the cosmos, the laws governing rotation are the same. The same figure skater physics that operates on Earth operates inside a star in a galaxy a billion light years away. And yet, within that symmetry, there is extraordinary diversity. Planets spinning in every direction. Galaxies rotating in their vast spirals. Pulsars turning hundreds of times per second. The Earth tilted at a particular angle, giving us our particular seasons, sustaining the climate in which human civilization arose. All of it is a result of the same conservation law playing out in different initial conditions. The law is universal. The outcomes are particular. This is, I think, one of the deepest things physics teaches us. The universe's rules, deep, invariant, unbreakable rules. But those rules do not determine a single fixed outcome. They permit an enormous space of possibilities. The history of the universe is the story of that space being explored, one collision at a time, one collapsing cloud at a time, one tidal interaction at a time. We live on a planet that spins because of a cloud that collapsed, that spins at a particular rate because of a moon that formed in a catastrophic impact, that is tilted at a particular angle because of all the subsequent violence of the early solar system. Our seasons, our tides, our days, all of it the result of specific contingent events playing out within universal laws. There is something in that thought that I find genuinely moving. The rotation of the Earth is not just a physical fact. It is a consequence of billions of years of history, conserved in the most literal sense, imprinted in the spin of a planet, and read out every 24 hours in the rising and setting of the sun. The universe has been spinning since long, before there were eyes to watch it spin, since before there were planets to carry those eyes, since before there were stars to light the sky. The first gas clouds, drifting in the dark after the Big Bang, already carried tiny seeds of rotation in their barely perceptible motions through the gravitational field of the early universe. Those seeds were amplified by collapse, inherited by planets, exchanged with moons, recorded in tilts and orbits in days. And some of that rotation, an unbroken thread, billions of years long, is in the ground under your feet right now. You are the universe spinning, not metaphorically, not as a poetic flourish, as a physical fact. The angular momentum in the Earth's rotation traces back, in an unbroken chain of conservation, to the motions of gas in a molecular cloud that existed before the sun, before the Earth, before life, before everything you've ever known. That chain has never been broken. That angular momentum has never been destroyed. It has only ever been transferred, reshaped, redistributed, and it carries within it, in the precision of its conservation, a kind of memory that stretches all the way back to the beginning. Everything in the universe spins, and everything that spins remembers why.